Welcome to your science class. Today we have an assignment. We need to calculate the velocity factor of this cable. The velocity factor is how fast does the electromagnetic wave travel through this cable in comparison to the speed of light in a vacuum.
Oh my god.
Yes.
Oh my god.
This is a 75 ohm cable. This is a 50 ohm setup. This is going on a 50 ohm transmitter. Why would somebody use a 75 ohm cable on a 50 ohm transmitter? Don't ask me. I'm not building the antenna. They just want to know the velocity factor. And I was like, okay, I can measure your velocity factor. That's not a problem.
Okay. Why is it important to know that?
To calculate how long the antenna needs to be, so you can tune it, so you can design it in advance using this cable, and then you can get it as close as possible, and then after you build antenna you need to tune it, but you need to be in the ballpark.
Okay. Is the length of the cable important? I mean, does it matter?
Yes. In that particular design it matters, but for our measurement it does not matter, because we are calculating it in percent of c, or the speed of light.
Okay.
But I do not know how long this cable is, so I will just measure the delay through the cable, and then I will give the cable back to its owner.
Okay, so your measurement does not depend on the length of the cable?
No.
Okay then.
I mean, you will get different time, but the velocity factor is the same regardless of the cable, because the speed, if the cable is constantly made, if nothing changes, the velocity factor should be the same.
Yeah, okay, I get it.
What are we doing? Let's draw it out.
Okay, I have more questions.
What questions?
What kind of cable is this?
This is a coaxial 75 ohm cable.
For antennas.
For antennas.
Okay, and why is it not already stated like on the cable, this factor?
Nobody stays with the velocity factor on their cables, because nobody gives a shit about that. Unless you're an antenna designer, or you're building some very fast electronics, and then you measure it yourself.
Okay, then you need some tools.
Yes.
Okay, what is this?
The tools you're gonna need: a signal generator.
This is something that antenna would generate.
Yes.
Okay.
And an oscilloscope.
Ooh.
You can do it without this, with a switch. But we
what
have
kind
this.
of switch?
Just you can just touch two cables together, but you need a 50 ohm resistor, and I don't have it here. What do we have here is, let's draw it. We have a signal generator, which is 50 ohm. Then we go through a 50 ohm cable. Oh, I don't know, I'm drawing this like this, to channel A. Yeah, this is a T junction. So this is a 50 ohm transmission line. I'm drawing it like this, which is very unprofessional, because we are mixing and matching lines. So this is a 50 ohm cable, and after the T, we are going to connect our test cable here to.
Okay, wait. This here is this cable.
This cable, yes.
Okay.
And we have a 75 ohm cable here.
So this is connected to this T junction. It's
Yes.
just this.
This
And
is
then
the T-junction.
And then it goes back somewhere here.
And then we are going to connect our measurement cable from here to here.
But where does it?
Wait.
Okay.
And then on the oscilloscope we will see the difference in time in nanoseconds. How long does it take for the signal to come from the T-junction to the second channel, the B channel.
Where is this channel?
This is the A channel, this is the first channel and second channel.
Okay, what are those?
These are just some crocodile clips so I can connect the test cable. So we have a very nice sine wave which is roughly 1 kilohertz. Oh, that is very stable.
Okay.
You don't need a very nice frequency for this. And then we're going to connect the middle part to the middle part and the shield to the shield.
Going like that.
Yes, it's very low tech. And that's it.
Okay.
And the other side, we're going to connect the shield to the shield and the center to the center. And we have something like this.
Wow.
And if you zoom in, you can maybe see a little bit of a phase change. Let me just put this one up here. Sorry. They're almost perfect, right?
Wow, cool.
But if you do this,
What did you do?
this is old. This is a square wave now. And then if you zoom in even more, and you position this at 0 microseconds, where is my trigger? And you zoom in.
Ooh. Really? Ooh. Okay, what is this?
So we can turn on the frequency, but that doesn't matter. So what we are looking here is a square wave comes to the A channel, and then it splits here, goes to the B channel. Because this is not matched, you can even measure this like with a short circuit, but we're not doing that. Then what we're looking at is, let me just separate them. The difference when does the B channel get up to the some voltage.
Okay, B is blue.
Yes, second channel is blue. So let me just put this at 0, and let me just put this at 0. And this distortion that you see, see how it overshoots, then it has a spiky and it has a wobble.
You just condensed it now a bit.
Yes, I just squished the signal so you can better see the overshoot of the the beach, and it goes like this, like this, like this. It goes like
okay.
that is because these are not impedance matched.
Okay, but also the first channel also does something.
Yeah, because of the cable. If you unhook the cable, you should get a much better signal. See?
Yeah. Okay. So it's better visible at this square type of signal.
Yes, because on a sine wave it's hard to measure. Oh, look at this catastrophe.
Oh, wow.
Yeah.
Oh, cool.
That is because
What do we see now?
you see now.
Oh, what?
This is
Ooh.
what you get when you don't
So cool.
when you don't impedance match your cables. Come on. No, on the other side.
Oh, wow.
No, the other side.
This looks so cool.
Yeah. So this is without ground connected. As a wave comes to the cable, passes through the cable, hits the end of the cable, then goes back, and then goes back, and then it oscillates. And if you move this, you can change the impedance of the cable a bit. This shouldn't be in a loop like this, I know. Can we change it by putting a metal? No. Okay, so it's not impedance matched, and this is why we have that oscillation. But that oscillation is not helping us measure anything. So we are just going to ignore it. Put a square wave. Put it like this.
Yeah.
And then you put both signals at the same place. Let's put coupling to AC. Coupling to AC. Yeah, that does not help me. So we put two signals like this. And then I need some math. Cursor.
Okay.
And I put one cursor 100 millivolts. Wait. So I match the zeros, and then I put one cursor about here.
What?
And that cursor is currently at minus 200 millivolts in minus 14 seconds. Then I change the cursor. How do you change the cursor? Oh, cursor 2. Move the cursor 2 to the same voltage. This is very stable. Where is my trigger? Let's put the trigger on a more stable part. Okay, cursor. Put the same there. The second. Zoom in. Enhance. Can I position this left? Oh yes, I can. Then I can zoom. Does this help me? Okay, so cursor 1, where are you? Cursor 1 goes where this line intersects with this part. With
This
this
background
on
line.
the scale, yes. So where this cursor intersects the... I want the intersection of the cursor 1 and the signal 1 on the minus 200 millivolts background.
Okay.
And then cursor 2, I want the intersection of the cursor 2 on the signal 2 on the minus 200 millivolts background. And one more thing that we can do. Wait. Measure? No. Acquire. Average. Yes. Oh, beautiful. Much easier to look at. Okay, so cursor 2 somewhere here. And this thing tells us automatically the difference. So this is at minus 2.4 nanoseconds from the trigger.
Yeah.
And this one is at plus 51.6 nanoseconds from the trigger on this side. And that gives us the difference of 54 nanoseconds. So delta T is 54 I really cannot write. 54 nanoseconds. So the signal that's going through this cable needs 54 nanoseconds to go from the beginning of the cable to the other end of the cable.
Cool.
Yeah.
Okay, what now?
Now we need to give this cable back.
You need to calculate something else.
I need to know the length of the cable. Because you need to divide the length by the length. I don't know how to say it, but I can spell it out at some point. Give me a second to clean this up. This is the value that we needed, 54 nanoseconds.
Cool.
So the signal propagation through this piece of wire takes 54 nanoseconds to go from one end to the other.
Okay.
That is what we needed.
Okay.
Now give me a second to clean everything up. Acquire sample, and then I will try to calculate the thingamajig. I will calculate the velocity. It's not that difficult. It's just like simple division. Don't worry. You're just messing with the speed of light. But that's it. We are done with the measurement.
Cool.
We need to pack this shit up, and then we are going to plug in some numbers into the calculator and see what comes out.
Okay, we'll be right back.
So the velocity factor is the percentage of how fast you go in comparison to light speed. A velocity factor of 1 is light speed. Velocity factor of 0.5 is half of the light speed. If you want to calculate the velocity factor of this cable, you have the following formula.
Yeah.
So velocity factor VF equals the length of the cable divided by the time delay through the cable times the speed of light.
Okay, just time delay.
Yeah, the delta T. That's
the
what we measured.
time needed for
signal to come from this side of the cable all the way to this side of the cable.
Okay.
Now, if you're not sure in the formula, this should be in percentages. This has no units.
Okay.
So this is meters. This is seconds.
Sorry.
Yes.
Percentage or like decimal, 0
Yeah.
something.
Yeah, it's just 0 point something. So this is meters. This is seconds. So that's meters per second times meters per second. Meters cross out second. Everything crosses out, and you get 0.
Yeah.
So if you plug in your values, and if you look at the cables, the cables have, this is 1 meter, so this was probably 0. It had a cap on. This is 1 meter.
Okay, and
this is 14 meters here, and let's say 15 meters here. So let's say it is 15 meters. So
this is
velocity factor
enough
for the demonstration purposes is 15 divided by 54 times 10 to the minus of 9 times 299,792,458
meters per second.
So the velocity factor is
15
54 times 10 to the minus 9 times 299,792,458. Let's see. 0.9265.
Okay, you could just take all these. Take your dot and put it here because you have 9
Yes.
places.
Yes, you can. Yes, but I wanted to spell it out.
Okay. We
And
have
that
what?
is
0, 9. This is 9.
92.65% of speed of light.
Okay. Is this good?
Nah,
Okay.
it is what it is.
Okay. Cool.
Now we need to bring that information to the designer of the antenna.
Okay. We did some math.
We did some formulas.
Oh.
Did we ever do formulas on this channel? Using math and electricity?
We can sometimes apply stuff we learned in school.
We did not learn this in school. This was just common sense. I never learned this in school.
Like velocity factor or
The velocity factor and measuring
or
this,
dividing.
dividing, yeah, that was a big problem. I was like, why do we have to do this? I have a calculator. You will never have a calculator in your pocket. You will never have a number, but fuck you, I have locally downloaded Wikipedia now.
Okay, bye.
Thank you for watching. Calculate your cables. Bye.
If you know how to, now you know.